Our first problem is to find or to calculate how many real roots will this particular polynomial have. Okay, the number of real roots of f of x equal to x raised to 6 plus x cube minus 1 is equal to 0, 2, 4 and 6. This is from our latest NEST paper, NEST 2023 shift 1, question number 2. Okay, now this is a 6th degree polynomial, right? This is a 6th degree polynomial. Even if this polynomial doesn't have x raised to 5, x raised to 4, x raised to 2 and x term, because the largest power is 6, we will call it 6th degree polynomial. Okay, and there is a theorem which we call the fundamental theorem of algebra, which tells us that if we have a polynomial which has nth degree, polynomial of nth degree, then it will have n roots in the set of complex numbers. Okay, so in this case the coefficients are all real numbers, but that doesn't always guarantee that all the roots of the equation are real numbers. They can very well be complex numbers, but we have to now guess or find out logically how many of them are real roots. Okay, so let us start solving. I hope the objective is clear. We would like to find how many values of x satisfy this. The largest it can be is 6, but out of those 6 things, how many are real roots we need to find it. Okay, so let's first write down the equation here. Okay, now quite often the very first step that we choose is important. We may solve this problem by trial and error method, but it's a bit difficult because we have got 6th power of x and then cube of x. But observe that x raised to 6 is actually square of x cube. Okay, x raised to 6 is square of x cube. So if I choose the transformation x cubed equal to t, just in case, okay, then our equation becomes t squared plus t minus 1 equal to 0. Okay, we have not yet solved the given equation, but we have transformed it into a quadratic equation by substituting x cubed as t. Okay, now can we solve this? Yes, we can solve this. What will be t? Minus b plus or minus root of b squared minus 4ac. Now be careful here. When I write minus 4ac, observe that the constant term is already negative. Okay, upon 2a. So this will be minus 1 plus or minus root 5 divided by 2. This gives me two values for t or for my x cube. First is minus 1 plus root 5 by 2, and the second one is minus 1 minus root 5 by 2. Okay, and now this particular pair of values can conclusively tell us how many real roots does our function have. Okay, so what is our objective now? Our objective is to now continue with two equations. What are those two equations? First is this one, right? First is this one, and the second is this. Now can you people tell me what numbers will satisfy x cube equal to something and x cube equal to something? Okay, first of all, did you understand this part? Everyone?
Yes.
Okay, now so that part is clear. Part 1. In part 2, we are in a situation which we have already been through in finding complex cube roots of 1. or what we call complex cube roots of unity, where we have x cubed equal to 1, right? And we know that for x cube equal to 1 there are 3 roots, out of which one root is real and then the other 2 roots are complex conjugates. And same thing is going to happen with x cubed equal to minus 1 plus root 5 by 2 and x cubed is equal to minus 1 minus root 5 by 2. The only difference is here we have got something else, but that is definitely not going to change the pattern of the roots. Now you might ask, why is that true? Consider y equal to x cube. Okay, if you consider this function y equal to x cube, and then if you take the root, you will realize, if you take the derivative, then you'll realize that this derivative is always greater than or equal to 0. And the graph of y equal to x cube also tells us the same story, right? The graph of x cubed is something like this. Okay, and this is 1 function now, which means no two real numbers have the same root, same cube, rather same cube. Okay, it's 1 1. Yesterday we saw it while quickly revising. So keeping all these things in mind, we can say with conclusive evidence that therefore x equal to cube root of this and x equal to cube root of this are the only two real roots. Other four will be complex conjugates. Now let's come to the Descartes part and verify whether those are indeed the real roots. Okay? X raised to 6 minus x raised to 3 plus 1. Oh, sorry, what's that? Plus x cube minus 1. Okay, so those are the two real roots, and we would also like to see whether our roots are correct. Cube roots of minus 1 plus root 5 by 2. Minus 1 plus root 5 by 2 whole raised to 1 upon 3. That's 0.85. That's this root. Okay, the positive root. And if I change this to minus, it gives me negative 1.17. That is this root. Okay, so that verifies our answer. I agree that my method was lengthier than the Descartes rule of signs. So it says that the number of real roots of f of x equal to x raised to 6 plus x raised to 3 minus 1 is, and if you remember, we got option B to be right. You got option B to be right. So if you go by this rule, it turns out that the solution becomes very easy. Okay, we can get it even within a minute. So, but to know that, you have to get the rule. You should know the rule. So the rule is something like this. The rule states that if the non-zero terms of a single variable polynomial with real coefficients are ordered by descending variable exponent, and it's already descending, it's 6, then 3, and then 0. So it's already descending. Then the number of positive roots, positive means x greater than 0, is, okay, now this is something interesting. It is either equal to the number of sign changes between consecutive non-zero coefficients, or is less than it by an even number. Okay, is less than it by an even number. Now let us consider the changes in the signs. Basically, we need to consider the coefficients. X raised to 6 is positive. X raised to 6 is positive. X cubed is also positive. And this is negative. So how many sign changes take place? Number of sign changes is 1. Is it clear? From positive to negative, only one sign change is taking place. Only one sign change is taking place. So if it is either equal to the number of sign changes or is less than it by an even number, if you decrease this by 2, it will be -1, and that will not make any sense because we are counting the number of roots, which means it has one positive root. Raise your hands if you agree to this. In particular, the number of sign changes is 0 or 1. So in this case it was 1. The number of positive roots equals the number of sign changes. Okay, so that's one positive root. But real roots mean it can also be 0 or negative. Clearly 0 is not a root. Okay, 0 is not a root. So whatever other roots it may have, they should be negative. Okay, now go to the third para. As a corollary to the rule, the number of negative roots, okay, the number of negative roots, which means x less than 0, is the number of sign changes after multiplying the coefficients of odd power terms by -1. Odd power terms, quite understandably so, because for even powers it will remain that. So if you now multiply the odd powers by -1, it will be positive, negative and negative. So what will change? Here it was positive, now it is negative. Okay? So the number of negative roots is the number of sign changes after multiplying the coefficients of odd power of terms by -1 or fewer than that by an even number. But again the number of sign changes is 1. Right? Positive, negative and then it's negative, so that will not count as a sign change, so it will again be negative. So one positive root, one negative root, so two roots. Got it?